Today in geometry, we looked at some theorems that follow directly from our understanding of similarity in triangles particularly, but in, well, actually it's not even just in triangles, but in lots of figures and similarity in general. More dealing with triangles than not, but some things that aren't necessarily just on triangles. So what we looked at were three theorems that are just sort of kind of really specific cases. The first one was the triangle proportionality theorem here, and we know from knowing these two are parallel that these pieces are going to be proportional. The reason for this is that if these are parallel, we have corresponding angles, and you could also say angle C is in both triangles, and so you have angle, so those triangles are similar. So just knowing that these two sides are parallel tells me that these pieces are proportional. Converse is also true. If I knew that the pieces were proportional here, the pieces of the sides, then I could also say, oh, those lines, those segments must be parallel. Or this side of the little triangle is parallel to this side of the big triangle. Okay, we did an example problem about that one. Here it is. We could set it up 8 over 4 equals 12 over x and then solve. Our second theorem we looked at doesn't really have a name, but I called it sort of parallels and proportional pieces. We have two transversals with three parallel lines crossing them, and basically they just cut those transversals into proportional parts, like A over B equals C over D, or you could also say A over C equals B over D. These pieces are just proportional to one another. And here was our example with that. We said that we could set this up lots of ways. If we take 20 minus 4, this is 16. So we could say 16 over 32 equals 4 over x, or 16 over 4 equals 32 over x, or 20 over 4 equals 32 plus x over x. There's lots of ways to set it up. All right, here is where we need to go last. The angle, this is not actually a name, this is just me saying angle bisector proportionality. This is basically about having an angle bisector and what it makes proportional. Now what I wanted to do was draw this for you as I read this to point out what it's saying, because sometimes you really have to sort of translate how theorems are written into what makes sense. So if a ray bisects one angle in a triangle, okay, so let's say I have a ray that bisects angle C. That would mean that it cuts angle C into two congruent half angles, basically, or halves of the big angle, two congruent smaller angles. So this is a ray that bisects one angle in my triangle. It bisects angle C. That ray, divides the opposite side. This should say opposite side, which would be AB. This is the side across from angle C, so it's the opposite side. It divides this side, let's call this point D, into segments, AD and DB, proportional to the other two sides. So what's happening here is it's saying it divides this side that it crosses into segments that this to this and this to this, okay? This side is proportional to this, or this piece is proportional to this side. This piece is proportional to this side. So they're proportional to the sides that they touch, or that's where the relationship is. So let's kind of color code this. What if I say this is kind of purple, this side, and I'm going to let this be purple also. And this is green, and this is green. Okay, so we could set it up as purple over purple equals green over green, or we could say purple over green equals this purple over green. There's lots of ways to set it up. So this is the one we want to try. Okay, so here's the angle bisector right here. So this is the side that it splits into similar, or excuse me, proportional pieces. So the 10 is proportional to the 8 in the same way that the y is to the 14, or the ratio 10 over 8 equals y to 14. Or you could say 10 over y equals 8 to 14. Or 14 over 8 equals y over 10. Lots of ways you can say it. Okay, whichever way you say it, you are then going to cross multiply to solve. And we'll get 8y equals 140. Dividing everything by 8. That's going to give me, let's see, we know it will reduce 35 halves, I believe. Or if you did that as a decimal, that would be what? 17.5? And that's all there is to that theorem. So again, if you have an angle bisector, it comes across and it cuts this side across from it into two pieces that are both proportional to the sides of the triangle they connect with. And that's all you need to know.